Welcome student. We have to see position of vibrational band in heteronuclear diatomic molecule in vibrational spectra. We already studied that in harmonic oscillator, if we plot a graph of internuclear distance and frequency in terms of wave number, then the frequency in terms of wave number, that is epsilon of or energy of vibration, then the curve obtained in such a manner. Here it is V equals to 0, first vibrational energy level. Later on it will be V equals to 1, later on V equals to 2, V equals to 3, and so on. Now when the molecule is in its ground state, and you know the general formula for energy of vibration is E vibration is equals to V plus half into H omega of oscillation. Here this is the frequency, vibrational frequency of oscillation. Now if we put, or if we have to calculate the energy of vibration in vibrational quantum number V equals to 0, then its energy will be epsilon 0 is equals to V means 0 plus half so many H C omega bar of oscillation. Okay. Now for here, if V equals to 1, then this epsilon 1 will be 3 by 2 H omega bar of oscillation, and later on it will be epsilon 2 equals to 5 by 2 HC omega bar of oscillation, and it will be epsilon 3 is equals to 3 means 3 plus half, it will be 7 by 2 H omega bar of oscillation. In this way this is about diatomic molecule. If we consider it as a, what we consider it? It consider as a simple harmonic oscillator. Now we know that the selection rule for absorption vibrational spectra is delta V equals to +1, and for this selection rule the possible transitions are from V equals to 0 to V equals to 1, or V equals to 1 to V equals to 2, and in this way V equals to 2 to 3, and after this V equals to 3 to V equals to 4. These are the possible transitions. Now here this first band is obtained when transition from V equals to 0 to V equals to 1, and it will be recorded as a single line. It is a fundamental band observed for this transition. Now for the transition V equals to 0 to V equals to 1, this is the fundamental band, and later on when for other transitions from 1 to 2 or 2 to 3 the bands are obtained, but the same position is there, because you know if there is a transition from 1 to 2 or from 0 to 1, then how it can be calculated? If there is a transition from 0 to 1, then nu bar is equals to, for this transition, epsilon 1 minus epsilon 0. What is the value of epsilon 1? It will be 3 by 2 hc omega bar of oscillation minus half hc omega bar of oscillation. Now in this way, this is the value of energy for this vibration. If we calculate it, then it will be 3 by 2 minus half. It will be h omega hc omega bar of oscillation. Now if for second transition, this is about the fundamental band. Here fundamental band is observed. Okay, now other transitions, let me consider 1 to 2, then nu bar equals to, what is it? Epsilon 2 minus epsilon 1. Again 5 by 2 minus 3 by 2. Then again 2 by 2. Then it will be hc omega bar of oscillation. Now here the same wave number is observed, means same bands are observed for further transitions, and in this way these transitions will give the band at the same position, and the position of the band here there is the same. That's why it is said that the transitions, fundamental transitions and other possible transitions are also there. Now for other transitions the band will be obtained at the same position. Now if we consider unharmonic oscillator, now for such a unharmonic oscillator the selection rule is delta V equals to, what is selection rule for anharmonic oscillator? For unharmonic oscillator. Now for this oscillator the selection rule is delta V equals to plus minus 1, plus minus 2, plus minus 3 and so on. Now when there is a transition, means plus minus 1. If it is absorption spectra, it will be delta V equals to plus 1. Now for this transition the band obtained is known as a fundamental band, and this fundamental band is a strong band, fundamental band, and it is a strong band. Okay, now for other transitions, let me consider a transition delta V equals to plus minus 2 or plus minus 3 for this selection rule. Now let me assume for absorption spectra delta V equals to plus 2 or plus 3. Now here the band observed are not strong band, they are weak bands. What will be observed? Weak bands will be observed, and for this weak band, if there is a transition delta V equals to plus 2, then it is called as a first overtone. What is it? First overtone. Then delta V equals to plus 3, then it will be second overtone. In this way, these are the weak bands, and fundamental band in anharmonic oscillator is strong band. Okay, this is nothing but weak, this is nothing but strong. This is about the position of the vibrational bands in heteronuclear diatomic molecule. So far as first case is harmonic oscillator, for that selection rule is delta V equals to plus minus 1. If absorption vibrational spectra is there, it will be delta V equals to plus 1. And for this transition, what is the position? The position is the same. Now here it will give the band at the same position. Okay, and that same position in the previous case we denoted it as a omega bar of oscillation, hc omega bar of oscillation. and later on after calculating E1 minus epsilon 0 E1 minus epsilon 0 epsilon 1 minus epsilon 0, or for epsilon 2 minus epsilon 1, you will get this line at the same position, and this band is a fundamental band and it is a strong band. But in anharmonic oscillator, in second case, the selection rule is delta V equals to plus minus 2 plus minus 1 plus minus 3. But for delta V equals to plus 1, the strong band is observed there and it is a fundamental. Now other transitions plus 2 or plus 3, it will be weak bands, and this is weak band for this plus 2 means it will be first overtone. Okay, now consider here what is which transition is there here. Suppose V equals to 0, V equals to 1, then V equals to 3, 2 and so on. Okay, now if it is so, then it will be fundamental band. Now if this transition is there, okay, plus 2, then it is first overtone and it will be second overtone. Okay, now position is different, not as that of the simple harmonic oscillator. Okay, now here this is about the position of the vibrational band in heteronuclear diatomic molecule. For this you must know the previous expression. Now you know previously vibrational energy is given by E of vibration is equals to V plus half into H omega bar of H omega of oscillation, only omega of oscillation, so many joules. Okay, now this expression you must know. Later on you must know when V equals to 0, it will be half Hc omega of oscillation. V equals to 2, it will be 3 by 2. Okay, this is known to you, then it is possible to draw that diagram, and from that diagram for simple harmonic oscillator, for diatomic molecule, fundamental band plus 1, delta V equals to plus 1. Okay, and for other transition from 0 to 1 and from 1 to 2 or 2 to 3, the other bands obtained at the same position. It is a strong band. Okay, same position is there. Now in anharmonic oscillator, different positions are there. Okay, because the selection rule is for anharmonic oscillator is in this way, and this is the strong band. It is a weak band. In weak band, for delta V equals to plus 2, the first overtone, it is called as first overtone. Delta V equals to plus 3, it is called as a second overtone. Okay, are you getting clear? समझ में आया ये सब?